imaging, phase and orientation mapping, spectroscopy in TEM and SEM coupled with cathodoluminescence, etc. And we'll discuss recent case studies from the field of cultural heritage. With no further ado, I would like to give the space to our first speaker, Dr. Partha Pratim from NanoMEGAS and Electron Crystallography Solutions. Partha is a chemist and with a PhD degree from ETH University in Zurich. His talk will be on electron diffraction in TEM to characterize cultural heritage materials from ancient Greek artifacts to Maya mural paintings. And the second presenter will be Dr. Eleni Palamara from Arte Solutions and also from the Laboratory of Archaeometry of the University in the Peloponnese. Eleni is an engineer with an MS from Oxford University and a PhD from the University of Peloponnese, and her talk will be on state-of-the-art electron microscopy techniques for the analysis of glazy materials and paintings, identifying raw materials and provenance. Partha.
Hello everyone, I am Partha. Thanks Nikos for the introductions and thanks everyone for joining the webinar on electron diffraction in TEM to characterize cultural heritage materials from ancient Greek artifacts to Maya mural paintings. As Nikos said, I started my scientific career with X-ray diffractions, and for last 8 years, I have been working on applying transmission electron microscopy for materials characterization and also developing new methods in this area. In the last 2-3 years, we got interested to apply transmission electron microscopy to characterize cultural heritage materials. And in these presentations, I will show some of our work over the last few years. I am a material scientist, not an archaeologist. So if there is any errors from the historical point of view during any part of my presentations, then I must apologize for this from the beginning. So I'm working in NanoMEGAS as an application scientist. In the audience who are not aware of NanoMEGAS, the company is based in Belgium and it was created in 2004. The company mainly develops hardware and software for applications in the field of electron microscopy. Our instrumentation is actually present in more than 200 laboratories and all over the world. And NanoMEGAS participates as an SME partner to the largest European project on transmission electron microscopy, STEAM3. NanoMEGAS is also an active partner for International Union of Crystallography for Electron Crystallography Commission. Though most of the audience, as far as I know, are from cultural heritage science, but for the people who are not from this branch of science, I took the definitions of cultural heritage as defined by UNESCO. The cultural heritage, as you can see, the cultural heritage encompasses several categories of heritage. It could be paintings, it could be monuments, or it could be even performing arts, or it could be natural heritage as well. And the preservations and presentations of the cultural heritage are a cornerstone of any cultural policy. So then to preserve or present any cultural heritage, one must know how to characterize it properly. There are several techniques are used to study cultural heritage materials, but one need to keep in mind the method should be non-destructive. The commonly used techniques are atomic force microscopy, computed tomography, CT for imaging, electron probe microanalysis, secondary and mass spectroscopy, atomic absorption spectroscopy to do elemental analysis. Also thermoluminescence, optical simulated luminescence technique are also used for dating. And also techniques like X-ray diffractions are used a lot in studying cultural heritage materials. There are also a lot of use of scanning electron microscopy, but there are only few studied cases by electron diffraction or electron microscopy in general. Two of the early papers, one in 2004 and 2016, I have shown in the slides. I've shown in this slide. The major reason probably, as most of the archaeological scientists, do not have an easy access of TM instrumentations. Probably one of the reason TM has not been majorly used to study culture heritage materials. But why TM is so important to be used to study culture heritage materials? As in TM, quantity of material, quantity of sample required is extremely small, and also it provides nanometer resolution information using TM studies. The people who have not seen that, who have not TM, the TM it looks like this. As you can see in the slides, the transmission electron microscope is a very powerful tool for a material science. Yes, it's an expensive tool, but it's very powerful. In TM, a high energy beam of electrons is passed through a thin sample, and the interactions between the electrons and the atoms are used to observe features in the specimen. Interesting part of the TM is one can do high resolution imaging of the material. At the same time, one can do diffraction to obtain structural information from the same part of the material. And one can also do chemical analysis like EDX, yields to find the chemical compositions of the material. The TM operates on the same basic principle as the light microscope, but uses electron instead of a light. Because of the wavelength of the electrons is much shorter than that of the light, the optimal resolutions obtained in TM images is much higher orders of magnitude than in a light microscope. So TM can reveal basically finest details of structures, in some cases as small as the individual atoms. Recently, laboratory of Archaeometry in Palamara, Greece, they have been, there is a new TM has been installed to study culture heritage materials. If any one of you from the audience have any questions related to this facility, one can contact Nikos or Eleni, who will be my next speaker. As most of the applications we have worked over the last few years is on electron diffraction, in the next two slides, I will focus how electron diffraction data is acquired in TM and what informations can be acquired from electron diffraction data. Most of you have seen a diffractions from X-ray diffraction instrument. Electron diffraction in a TM instrument works in a very similar manner. Major difference in a TM is one can study very small quantity of materials, and one can also focus the beam to get diffraction or images from a very small nanometer size crystals. There are different methods of preparing sample for TM. It could be by simple grinding, or it could be by FIB or by ion thinning. I'll show you some examples when I show some of the case studies. Usually the sample is mounted on a 3mm TM grid, and then it is fitted on a TM holder, and then one need to insert the sample holder in the TM, as you can see marked in red. That's where the sample holder goes, and then it is ready for the TM observation, TM observations. Usually first in the image mode crystals are checked, and then one can use diffraction mode to collect diffraction data. The simplest methods for the diffraction is one can compare the obtained diffractions with the simulated diffraction pattern from the possible known phases, and if it matches with the simulated diffraction pattern, then one can confirm the presence of a particular phase. And in this example from a cubic mineral, you can see where the experimental diffraction pattern was compared with the simulated diffraction patterns, which is simulated diffraction pattern in the bottom, and the obtained pattern matches with the 111 zone axis pattern of that particular mineral. Okay, but if the phases present in the material is unknown, then there are other methods to extract structural information. The methods known as 3D electron diffraction tomography, or in the recent literature as micro-ED. To acquire data from a three-dimensional electron diffraction data, one need to find a crystal in the TM grid, which is beam transparent and separated from the other nearby crystal. Only then one can collect the data either by tilting the crystal in fixed step size or with continuous rotation of the crystals. During the tilting of the crystals, if the sample moves away from the beam, then it is readjusted manually. And once the process is finished, a three-dimensional ED data is acquired, as you can see on the right-hand side. And then from the obtained ED data, one can obtain positions of all the atom in 3D space for an unknown phase. The data acquisition process is highly reproducible and robust, but it may take from a couple of minutes to several hours, depending upon the complexity of the materials. There are different variations of the same technique. We'll call all of them and 3D electron diffraction or 3D ED throughout all my presentations, and one can see more details about these methods and its terminology on a recent articles in ACS Central Science. Okay, now comes with the example. The first example is studying the pigments responsible for the color in a nearly 5th century BC glass amphoris. The sample was excavated from south of Greece. First, we have done EDX and EPMA analysis to find the chemical compositions of the pigment. And we observed, except the usual component present in a silica glass, we have seen traces of titanium oxide and cobalt oxide and copper and titanium oxide, cobalt oxide, and copper oxide. But the most interesting part comes in the next step. Okay, the sample was prepared for the TM experiment by ion thinning, and 3D electron diffraction data was collected. And from the 3D electron diffraction data, a hexagonal cell was obtained. And based on the obtained cell and the chemical analysis, which I have presented, the chemicals which I have presented in my last slides, we have looked into the structural database, especially from the ancient period, to understand which phase it actually belongs to. There are two blue pigments which we can see in the literature. One is Egyptian blue, other one is the millerite or osmillerite mineral. As the structure is hexagonal one, first option we can discard it. Interestingly, the same hexagonal mineral is also been found in the 1130 BC scarab of Egyptian origin in Sardinia, Italy. As the same mineral was found in Greece, possibly there was a trade route between Egypt, Italy, and Greece in this period, and this can also be confirmed from the literature. This work we have published in a recent article of Scanning in 2019. The second example is studying pigments in Roman tessera. A large collections of late Roman colored mosaic glass tessera excavated in 2008 at the sanctuary of Serapis within the archaeological site of Peloponnese, was first analyzed by Nikos and his colleagues by ACM and EDX to characterize the glass compositions and the pigments. After that, we have studied all the glass tessera to exploit novel by using novel electron microscopy and electron diffraction techniques, which allows basically obtain accurate structural information regarding the crystal structure of the pigments or the opacifier of the glass mosaics, and more specifically to study their compositions, crystal structures, and its relationship with the glass matrix. There are 6 different glass tessera which we have studied, but in these presentations I will only present about the results from the green color tessera. The sample was prepared by FIB, actually thin electron beam transparent lamella of 5 by 5 micron and approximately 50 nanometer thick sample was prepared by focused ion beam or FIB, and those thin slices of FIB card actually comes from a large tessera. The sample was lifted from the FIB on a specific FIB to a specific TM grid for subsequent TM observations and experiment. The same procedure is followed for all the remaining glass tessera sample, which I'm not showing here, but which you can see in the published work of this. Okay, the first part is the chemical analysis. The chemical compositions from the polished cross sections thin samples were analyzed by EPMA and STEM EDX in TM. And STEM EDX mapping and the EPMA both shows presence of shows the crystallites content lead, Sb, oxygen as major element, and also presence of copper, iron, tin, calcium. But why we have used both the analysis technique? The STEM EDX has a very high spatial resolutions, 3 to 5 nanometer, where EPMA has a close to 1 nanometer spatial resolutions. However, EPMA EDS has much higher energy resolutions, 5 to 20 EV, in comparison to 130 to 150 EV for a STEM EDS in the TM. So we believe for this type of study, it is very useful to combine both type of techniques like STEM EDX and also EPMA to find the compositions of the crystal. Okay. And also, as the FIB sample holder are mainly standardly made of copper, to ensure, because we have observed copper, to ensure that copper is contained only in the sample, we performed EDX in the ACM, and we saw close to, both from the matrix and also from the precipitate, and we saw close to 3% of copper present in the glass matrix and also from the precipitates. You can see the precipitates are of white contrast in the left-hand side in the ACM image. Okay, and in the next step, we have collected 3D electron diffraction data from the small precipitate. The precipitates are crystallines, but the glass matrix are amorphous. From the 3D electron diffraction data, unit cell was determined, and it is cubic phase center. Then atomic structures of the phases was determined, and the phase is a lead antimonade. But now we know the structural informations of the precipitate phase, but why this particular mosaic glass structure is green? And as a lead, we know the lead antimonate is of yellow color. There could be two possible explanations. From the chemical analysis, cobalt was detected, as you have seen in my last two slides. Combinations of blue color, cobalt with the yellow pigment, possibly one of the reasons for the green color of the glass. Other possible explanations could be opacifier structures are, as this lead antimonate is a pyrochlore, and ionic substitutions can happen in these pyrochlore structures. So this copper green color could be a result of yellow lead antimonate particles which may contain copper in the disordered side of the structure. These results has been published in 2018 in Heritage Science Journal. So you will be able to see not only the study of the green color tessera, you'll be able to see the studying of the other tesseras as well. The third methods, the third example, and the other second method, actually the third example, which we have used to study culture heritage materials, is called orientation and phase mapping. The technique is performed through automated collections of electron diffraction pattern on an area of several nanometer while scanning the area of interest with a nanometer size. The collected ED patterns were then fitted through the template matching, as you can see in the right-hand corner, with the pre-calculated theoretical patterns. And then then you can assign a phase and an orientations for each pixel positions, and each pixel colors corresponds to a particular orientations in the stereographic triangle. Typical areas of several square microns can be examined to obtain orientation and phase maps from all the known crystal phases within an examined area. To perform this type of analysis, one need a scanning unit, which is provided by NanoMEGAS, and a fast camera to acquire the diffraction data. But one need to keep in mind, to apply this technique, you need to know the phase informations of your studied materials. So using this phase and orientation mapping technique, we have studied pre-Hispanic Maya pigments coming from the Mayapan side in Yucatan Peninsula, Mexico. Several pigments with different colors have been analyzed, blue, green, and red, in order to understand the nature of the materials used for their preparations. Here I'm going to talk about only about the red color pigments. Detailed phase mapping by the STAR technique confirmed the presence of the hematite as one of the major components for the red color pigments found in the round temple or fisherman temple. On the other hand, solar temples, as you can see in the left bottom corner, presence of only cristobolite was found. In addition, you can see in the round temple or in the round temple that presence of nanocrystalline rutile was detected, which was not previously undetectable by any X-ray studies. So that's quite an interesting result. So then we have also done STEM EDX to confirm the presence of titanium oxide, and this obtained results is quite interesting, because the rutile impurities could come only from the mineral products extracted from the red soil from that region. Because these results from the STAR phase mapping, it demonstrate how precise a technique could be to analyze the prehispanic pigments. And hematite's iron oxide presence gives the red color of the pigments. That's responsible for the color. But mahamite, iron oxide also, which is we have seen in the phase map could also contribute to the red color. These results on the studying the pigments has been published in a 2019 scanning paper. You can see more details about the study of the other color pigments. So, and all these three articles which I have presented, it's here. You can see the published work. You will be able to see all the studying on the glass amphoris or on the Maya paintings or on the glass tessera. So now the important thing is to why TM is so important. TM is so important because couple of reasons. Because as it's a quasi non-destructive technique, and it needs only very small quantity of materials for doing any diffraction studies, be 3D electron diffractions or two-dimensional electron diffraction or phase and orientation mapping. And it can provide nanometer resolutions information which cannot be obtained by any other existing techniques. So then I would like to thank all the collaborators with whom we have worked from the different projects. Especially, I would like to thank Nikos, who is a moderator of this webinar, and also Eleni for the discussions and the collaborations, and to invite me to give presentations on the work which we have done. And I would like to thank you for all of your attentions and to listen, to participate in this webinar. And now I will pass to my next speaker, Dr. Eleni Palamara, for the next presentations on studying cultural heritage materials. Thank you.
Hello everybody, good afternoon. I hope you can hear me clearly. So following this excellent discussion by Dr. Das regarding the potential of transmission microscopy and its vast area of applications in cultural heritage, I would like to move us back to something that most of us are more familiar with, scanning microscopy. Only scanning microscopy with a twist. So I would like to discuss a combination of scanning electron microscopy with cathodoluminescence. Now, this is not a new technique. It is not even a new technique in cultural heritage. It has in the past been applied primarily to study calcium-rich or silicon-rich materials, and in particular for provenance analysis. However, we feel that the potential that this technique has in cultural heritage is vast, and it is not proportionate to the work that has already been carried out. So I'm going to summarize some of the work that we have been doing the past couple of years. And before I do that, very quickly, I would like to go through the basics of cathodoluminescence, which some of you may not be familiar with. So cathodoluminescence, apart from being a very large word, is a light or electromagnetic radiation ranging from the ultraviolet to the near IR. And it can be generated within an SEM chamber from the interaction of the electron beam with any kind of a crystalline material. So when an electron of our sample is excited, then as we know, it will return to its ground state, and then it will emit energy. Part of this energy will be emitted in the form of light. And the interesting thing is that the wavelengths of this fluorescence emission will be characteristic of the structure of the crystal. If we apply this, let's say, for example, to minerals, the mineral can have various defects on its crystal structure, which have resulted from specific conditions during its mineralization. Each of these point defects will create a different kind of a change in the crystal structure, which in turn will result in a different CL spectrum being formed. So in very simple terms, if we study the CL spectra, then we can have information on the history and the mineralization history of our sample. And to take this a step further, this means that using the CL spectrum, we can identify individual raw materials. In certain cases, we can examine their provenance. And also, in certain cases, we can also examine parameters of the manufacturing technology of these objects. So, what kind of results we get from this technique? In order to give you a very quick example, these are some analyses that we did on samples from black glazed Hellenistic pottery. We analyzed the glaze. As you can see here, we have two representative glazes. One is very nice quality black and shiny glaze, and the other one is cracked, it's brown, its quality is poor. Since we have the SEM, we obviously have the secondary and the backscatter imaging, and combined with the CL, we also get a different kind of imaging. These are called panchromatic images, and they show all the areas which are going to emit light, basically. This is both a way of identifying how homogeneous is our material in terms of its structure, but it is also a way, obviously, to have a better follow-up analysis. And then, again, we are talking about SEM with EDS, so we will have the elemental analysis. But parallel to the elemental analysis, we can also have the CL spectrum, which you see here. And each one of these bands correspond to a different emission of light. In this case, our result was that we could identify between the different, in a way, identify between different qualities of glaze based on the CL spectra, even though the elemental analyses were identical. Now, let's move to a better example of the application of CMCL. This is an effort that we have started in order to apply this technique for the provenance of glass samples. And we first applied the technique on archaic Hellenistic classical glass vessels, which were provided by Dr. Economou. These samples all have the same color. They're the very typical blue core-formed vessels of that period. They are identical in terms of typology, of decoration. They have very, very similar major and minor composition. And when we did the CL analysis, the result was that there were some differences that could be noted between the spectra produced for the two different sites. These are some indicative spectra, and you can see that the overall appearance is different. Now, this work is at its very early stages. We have only analyzed a few number of samples so far, and originating from a small number of sites. So it's very early to say that that this technique can work in all cases. However, it does have promising results, and it does show that there is a lot of promise there to identify between materials that seem to be chemically identical. Now, I would like to focus on something completely, on a completely different type of material. And I would like to discuss about pigments and painting layers. For all of you who have worked with painting layers, you know that is one of the worst types of materials to work with because they are very, very complicated. They contain a very wide variety of different materials, both organic and inorganic. We have layers of a mixture of different paints, a mixture of paints and other materials like binding materials. And of course, we have weathering, which we know can affect greatly both the visual traits and the chemical traits of the pigments. So first of all, we started with the analysis of individual pigments just to see whether we can differentiate between them. And the technique seemed to work very well, both with organic pigments. You see here some indicative spectra from organic pigments, and also from inorganic pigments. For example, here you can see that we can differentiate between a red ochre and a yellow ochre quite clearly. Also, the technique has good results in differentiating between chemically similar or chemically complicated pigments. For example, we can see very clearly the differences between the spectra of lithophone pigment and zinc oxide and barium sulfate, all of which contain basically the same ingredients. Now, the next step of this work was to try and see what happens when we combine these pigments with the binding material, because of course, for example, in oil paintings or in frescoes, we very rarely have a pigment on its own. So here we have an example of the analysis of white lead on its own, and then white lead combined with a number of different binding materials, walnut oil, linseed oil, and egg yolk. And as you can see, the good result is that the main bands of white lead do not change when it gets mixed up with the binding material. Although I have to say that I was a little bit disappointed that we could not also differentiate between the binding materials. However, the fact that our analysis is not affected by the binding material is, of course, very promising. Another test that we are carrying out right now is to see what happens with weathering. However, we do not have any results yet. We will very shortly. This is all very nice when it comes to analyzing individual pigments, but can this technique actually work when we have a real case scenario, an actual painting? So in order to have a first test, we were provided with samples from these two 19th to 20th century oil paintings by the National Gallery in Athens. We got some samples, some cross sections with multiple different painting layers. So the first good result was that we could identify the pigments, the main pigments that were in its layer. For example, here you can see in the spectrum that the analysis that we got from the painting, from the lead white on the painting, was very, very similar to the one from the clear lead white grains. The other thing that was very, very useful was the possibility of doing parallel mappings. So, for example, we identified grains of zinc oxide. And as you all know, we can have an elemental mapping and see what is the distribution of zinc in the examined surface. But the other thing that we can do is this is the equivalency spectrum of that grain, of the zinc oxide grain. And as you can see, it basically has two main sharp bands, one at 375 and one at 760. So the other type of mapping that we can have is to have an image where it shows us where on the surface, where are the areas that that emit light at 365 or 7060. In that way, we get not only a mapping from an elemental point of view, and a mapping of the distribution of zinc, but we also get a mapping of the crystal or the molecule that we are studying. So combining both of them in the exact same area can be a very nice, very quick way of characterizing our material. Also, because as I told you, we had multiple painting layers. This is an example. There were 8 painting layers as were characterized by optical microscopy, and with the backscatter image of the SEM, most of those layers could not be as clearly identified. And the bulk, let's say, spectra from those painting layers, the bulk CL spectra, could identify between the different layers. So not only can we identify the material, we can map the distribution of specific minerals, and we can have an added tool in order to differentiate between different painting layers. So all in all the work that we have done so far with this technique, it suggests that it can be very, very useful in cultural heritage, specifically the fact that we have a combination of elemental analysis and the luminescent analysis, which directly shows information about the structure of the crystal. And of course, the fact that all of that is done in micrometer level, so we have a very, very high resolution. Obviously, in order to do this technique, I forgot to mention that we can have a sample prepared in the same way that we would prepare it for SEM analysis. Especially when we're talking about materials like painting layers, the biggest advantage is the fact that we can tackle both organic and inorganic material at the same time with the same technique. The only disadvantage that this technique has, not the only, but the largest disadvantage that it has, is the fact that so far there are limited databases for material that is useful in cultural heritage studies. Which is exactly why we are open to any kind of collaborations in the future with any kind of material that could be useful in order to improve our databases and expand the applications that we can have with this new technique. From my part as well, I want to thank you for taking part in this webinar. I think we can now move to any kind of questions that you might have.